so I shall return. Okay, again, let me introduce y'all and say good morning for lesson number 4 of Engineering 1330, Computational Thinking and Data Science. The first question can be answered in the chat or by voice as you're remembering to mute yourself. Can you hear me?
Yes.
Okay, 1 yes. So 53 to go. Okay, that's looking good. Excellent. Great. Well, the topic for today is loops or controlled repetition. It goes under a lot of different names, and it's probably the key computational feature that we leverage in our daily personal and business lives that make computers so useful to us. Is their ability to do a particular sequence of tasks over and over again without complaining, except when you don't give them power, then they complain by shutting off. Can I mute everybody? I'd be happy to mute you. That is the... Oh, I can't do a thing unless I move your... Now it... we are going to mute everybody. There, you've all been mutated. Hopefully that didn't hurt too much. I mean, moving that DNA around, it always makes me a little nauseous. But I'm trying to get... I'm going to shrink that because that is always annoying to me. It's unfortunate because we won't see each other. Okay, I have my video turned off today for no particular reason, although I still have not diagnosed why my web camera is not behaving. I assume it's a maintenance of profit feature in the actual device, and I haven't provided profit to the manufacturer recently, so they shut it down remotely. Continuing on with today's lesson. So it's 8:04. Still people joining. I wonder if those are rejoins. It's amazing. So to return, controlled repetition is one of the key features of computing devices that we're able to leverage to make our lives better. It's an old joke that if you can do it with pen and paper, you don't need a computer, and that's indeed true. But if you have to do it 100,000 times, it'd sure be nice to pawn that activity off on someone or something else. And that's, keep that in mind as we work through today's lessons. So the topical outline for today is generically called loops in Python. In the lab and in some of the examples, I'll try to refer to a more historical terminology. Controlled repetition is what I was taught a long time ago, back when dinosaurs still roamed the earth, and a pterodactyl was a fine catch for a Sunday dinner. But we're going to examine... When I was preparing this lesson, I was going to try to demonstrate do loops entirely with conditional statements. But Python, by design, doesn't have a convenient way to jump over portions of code. It's a go-to statement in older programming languages. It's been proven that you don't need go-to statements to make effective programs. I downloaded some hacks to try to simulate that, but I couldn't get it to work right. So in the olden days, when you could jump from one section of a program to a different section, you could construct loops without formal for loops or while loops or do until loops using conditional statements. It was ungodly inefficient. So other than using it as a way to demonstrate that a loop is really just a logical structure or a conditional structure, there's no benefit. So I suppose it makes sense that it's no longer part of the language. We'll examine the for loop and the while loop. They accomplish the same thing in a different way, and there's no advantage of one over the other, except that usually the for loop is easier for a particular type of situation to implement, and the while loop is easier for the other type of situation to implement. Then we'll examine the concept of nesting. So loops can be built inside of loops, and we'll examine the concept of conditional statements within a loop. So a loop can do stuff over and over, and one of those things it can do over and over is test conditions and adjust program flow control based on the results of those tests. So our formal learning objectives are to understand the concept of loops, which whether you know it or not, you already understand the concept, and to understand loop types that are available in Python, and to implement the loops in some various examples. I have gone ahead and in my instance of CoCalc, I have downloaded, oh my bad, bear with me for a minute, and if you're trying to follow along, just watch. There's this worksheet here called Python Loops, IPYNB. Those are my examples that we do in the lection part. We can actually look at them in HTML. So I'm going to demonstrate the for loop, the while loop, and so on. And these are just rendered notebooks, so the HTML isn't terribly useful for you, but it's pretty valuable to me. Clicked on the wrong thing. I want this one. There we go. That's what we'll do in the lesson part. And then Lab 4 builds upon these ideas. You really just get to practice them. And then there's like 4 or 5 exercises in Lab 4. And like the other ones, they're essentially their homework. So you do as much of them in lab time as is feasible, and then you do your rest on your time. So as a computational thinking concept, a loop is very much related to pattern recognition. So you recognize a pattern in a process that you have to do something over and over again, and that recognition implies looping, and then that would be used in turn to design an algorithm to accomplish a task. So what's a loop as far as coding is concerned? A loop is the action of doing something over and over again, hopefully getting different output, because if you do the same thing over and over again, you get the same output and you're expecting different. That's the definition of insanity. Doing something repeatedly. A loop repeats a section of code or a set of statements a certain number of times, either predetermined or determined during the process, until it's complete. So you either exit a loop by breaking out of it when a particular condition is met. You exit out of the bottom of the loop, which is normal termination, because you've done all the steps that you intended to do, or you exit by exception. An error occurs, and unless you trap that error, everything just stops. So repetitive tasks are very common and essential in programming, and they save time. Ultimately, they save time in coding and minimize the coding errors. So think of trying to make a lot of something. So in doing that, you do things over and over again. So let's imagine we're going to prepare a peanut butter sandwich, which is the analogy here. So to make a peanut butter sandwich, to make one, not to get one. You don't walk up to the counter and say, I'll have a peanut butter sandwich and hand them your Apple Pay deal. Although that's a whole lot easier from an end user perspective. So you start the process, you assemble the required ingredients. In this example, you get a knife, you spread the peanut butter on one slice, you spread the jelly on the other slice, You put the two things together, you have a sandwich. So this block diagram that's on the screen, that might be something that you would use if you were operating a peanut butter sandwich restaurant and you had to hire employees, and the only ones you could get weren't necessarily the most self-starter in the bunch, and so you needed to provide on the employee counter where they do the sandwich assembly the steps that are required. And we can sort of laugh at that, but if any of you all worked at Subway, the assembly sequence is literally an algorithm to allow them to assemble a lot of sandwiches quickly. So let's suppose you had to make 1,000 peanut butter sandwiches. You would want to automate that block diagram in such a way that you just do it over and over again, and that would be considered looping. So in the comments, someone worked at Firehouse, and yeah, that counts. You probably had flow diagrams of how to assemble food products for the customers. Ultimately, anything that can be done in a loop, you can unroll a loop, and you could do them as single steps. But imagine 1,000 peanut butter sandwiches as an example. Let's suppose there were Python statements to do these different steps. So we have the start statement is irrelevant. 1, 2, 3, 4, 5 statements or actions are required to make this peanut butter sandwich. So to make 1,000 of them, we could repeat those 5 statements with cut and paste 1,000 times. That would be a 5,000 line section of code just to make 1,000 peanut butter sandwiches. And if we wanted to scale it, if we wanted to make it fewer or more, we would have to delete or add portions of code. Whereas in a loop structure, which is just a programming structure, we only have these 5 statements, and we have a mechanism called a loop that allows us to instruct our sandwich assembler, implement these 5 statements in order, repeat that 1,000 times. Later on, repeat it only 700 times. Later on, repeat it 1,100 times. And that block of code, if you will, is only those 5 statements plus whatever wrapper there is for the loop, which is just a few. So you can replace 5,000 lines of code with 7 lines of code. And that's the attractiveness from the programmatic maintenance perspective. Some of you will luck into having to maintain current and legacy programs, and you will appreciate that years from now that the programmers used programming structures to make it easy to maintain. At the time they did it, they weren't making it easy to maintain. They were being lazy, which is usually a good thing in that context. There are 2 major types of loops that are in the Python base language, and one's called for, the other one's called a while loop, and they're used commonly in 2 slightly different situations, and it'll make more sense when we get to the examples. The first is a for loop. So it has a few parts. It has a counter, or in this case it's called iterating variable. That iterating variable can either draw its information from a sequence that already exists, or there's a particular function to build a sequence. So it has this counter, and it has a stopping condition. It means once the counter is bigger than a particular number, you can quit the loop. And then there's the actual statements within the loop that get done. And in terms of a flowchart diagram, so we set the counting variable in the sequence, and so the sequence could be 1, 2, 3, 4, or Fred, David. It can be an iterable. It could be Fred, David, Judy, Bobby, and it will count through those. But let's say the iterating variable in sequence 1 to 4. So it's going to set the value of iterating variable equal to 1, and then it's going to test. Is the iterating variable larger than the biggest number in the sequence? If that's true, then we exit the loop and continue on with code execution. Alternatively, if the iterating variable happens to be a list of some kind, it's going to ask the question, have I reached the end of that list? If the answer is yes, again it skips over and moves on with the rest of the code. If the answer to those two is no, then it will execute a set of statements, increment the iterating variable by 1, either by 1 the number or move 1 over in the list, and then re-ask the question. And so it'll do this until it has used up all the items in the sequence. In the older times, that would be called an increment skip if greater structure. So that's a for loop, and the syntax looks something like this. For the item in some collection, execute statements, otherwise execute other statements. Oh, I apologize. The way I usually use it is for an item in a collection. The colon is part of the for loop. There's an indentation right here. Execute statements. We can use the else condition if we want. I find personally that unless it's absolutely necessary, it clutters up the code. And if the collection is a list or a tuple, the loop steps through each element of the sequence. So here's an example for C in the list 1, 2, 3, 4, 5, print the value of C. That's something we could actually try real quick as an example. And if the copy paste doesn't work, I can type fast enough to do that. So let's go ahead and Python loops, yeah. Okay, so that's taken straight from the presentation. And let's examine this before we run it. Okay, so C is the indexing variable. And the list that's in this case being indexed is the list 1, 2, 3, 4, 5. And what this loop will do is it will print the value of C to the screen. I'm going to add a single line. So this is outside the loop. Something like that. That's just to tell us we've exited the loop, and I'm going to print this. Okay, so a little minor change to what's in the presentation. And let me run that. So what do you think is going to happen? Oh, it looks like everyone wants to do an infinite loop. I'll create one for you in a second, because that's one of my favorite things. And I'll do it on CoCalc so that we're burning up time on their server. So what do you think is going to happen when I execute this script? Anybody? Unmute yourself and just describe it by voice. Don't try to type it.
So what's going to happen is it's going to print C equals 1, C equals 2, C equals 3 until it stops at C equals 5.
And then it's going to print the loop is over because that's what I told it to. Correct. Okay, let's see if I got it right or not. Invalid character in the... Oh, I know. So here's the danger of cut and paste. When you cut and paste stuff, it's not going to necessarily render certain characters correctly. I think if I do that, there we go. Yay! Okay, exactly what we said. And let's see if I have it. Yeah, I'll do infinite loops when we get down here to the while loops, because it's really easy to create an infinite loop with a while loop structure. It's actually easy to do it in for loop, but I don't want to do the thinking. So, okay, so if that collection is a string, then it steps through each character of the string. Let's test that conjecture. So we'll make a collection. We'll use Texas Tech University, just like this example. Although I have no action, it should print each character. Oh wait, let me put it in the right place. And I need to turn that into a string. And hopefully, I haven't made a unanticipated syntax error. And now it returns the contents of the string. Actually has some pretty interesting behavior because it even includes the white space, which are characters as far as the computer is concerned. If the elements of the collection are collections themselves, then the item would match the structure of the elements. So for example, in this case, it's going to print the contents of this list I'm about to create. And we need to turn these into proper character strings. Well, I didn't want that to happen. Okay. See, this person's using double quotes, so we'll follow that. All right, here's what I think is going to happen. It's going to produce 3 output lines plus the loop is over message. And the first output line will be the word first. The second will be the string first. The second will be the string second. The third will be the string third. Or it's going to give me pink screen of death. It did what I thought it would do. So there's an example of 3 different contents that the sequence can be built from. So a lot of times we're doing arithmetic work and processing the elements of a string or lists of strings is kind of stupid. Instead, we want to perform the loop a prescribed number of times. And in doing that, we would leverage something in Python called the range function. So here's one instance of range function. And we'll see, make sure, yeah, okay. So this, if you go to the Python documentation, it should introduce the range function like that. So by default, the range function has 3 elements that you provided: a starting value, an ending value, and the incremental step. So if the starting value is 1 and the ending value is 10, as shown in this particular example, and you're stepping by increments of 2, it should produce a 1, 3, 5, 7, 9. The next increment, which would be 11, is bigger than 10, so it exits the loop. So all range does is return a sequence of numbers. And range is a pretty interesting function because if we just print range 1 to 10, it gives kind of funny output. So this particular one will repeat the range function. We'll run the range function and it will produce an output, and I will actually create a new input. Okay, if we run that loop, it's going to produce a sequence of numbers 1 to 10. So let's test that conjecture, 0 to 9. But let's modify range. Let's say I want it to go from 1 to 10. And it still does 0 to 9. Now, why does it not print the 10th element? Silence.
Because the range isn't inclusive of 10?
Correct. It's the way Python default counts. So it counts from the starting position up until the end position, but it does not include the end position. Although we can trick it, and that should produce the 10. And the reason I put the +1 in there on purpose. So now we can make, well, actually that's nice and recursive. That will cause, do a little coding here. So we'll add a line and we will define the values of start. So anybody have a favorite starting number? Integer, please. Anywhere from -infinity to infinity, but not the two endpoints. Okay, so someone wants to, God, nobody does minus numbers. They're all a bunch of wimps. And we'll go from -4. And notice interesting syntax I'm using. In certain instances, it's convenient to do assignments on a single line. And the way I'm doing that is with this semicolon. Okay, so let's see. Maybe I'm more of a positive person rather than negative. Fair enough. For that response, we'll use your number as the upper limit. Actually, I hope the standard input-output can manage this. So here's what it's going to do. It's going to start counting from -4, and it's going to end at, the end value will be 1002, but it will end at 1001, and it'll print those, and actually that was pretty impressive. Now we have to scroll up for miles to get back to the beginning. Okay, so I will regret doing that. Let's do something a little more manageable. There we go. So -4, -3, -2, -1. So that's the range function. The third entry point in the range function is, I'll call it the increment. We can tell it how to do that counting. So we can count by ones, which is default. I have no idea what will happen if I put a 0 in there. We'll try that in a second. We can count by 2s. Let's count by 3s because that's different than the other two. So if we count by 3s, we get -4 plus 3 is -1 plus 3 is 2 plus 3 is 5 plus 3 is 8, and then the next 3 takes us beyond the ending value, so it exits the loop. Now, just for grins, I want to see what happens with 0. I think I'll get an exception warning. Yeah. And it says argument 3 of the range function must not be 0. So that's what I expected to happen. Let's see if we... Okay, so I said we're going to do an infinite loop. If this increments the way I expect it to, it'll never get to the end because we're going in minus. And let me find my way. I want to remember how to interrupt the kernel. Okay, it'll be up there. So when you create an infinite loop, which is generally a dumb idea, you need to have some way to stop the process. And so what I'll use is, once it starts infinite looping, we'll let it run for a few seconds, but I'll interrupt the kernel. I don't want to run it too long. It won't hurt anything. It just turns electricity into heat. But I would imagine that on the back end at the CoCalc server farm, they have management scripts in place, and it's going to disconnect sooner than I want to if it detects a process that never ends. So everybody ready to see the infinite loop? Okay, I'll take that as a yes. Do not try this on your machines, please. Because, okay, here goes nothing. And let me see. Yeah, it's running the script, and it appears nothing's happening. It can't get to the end of it. So the way it's doing it is it's printing to the stack, and it won't print until it exits the loop. So I'm going to restart the kernel anyway. So let's get our increment back to 2. Hopefully it has restarted. Save it. And there we go. Infinite loops, you should avoid them. And that was our first example of it. All right, let me return to the lesson. So we've pretty much beaten this slide to death, and this one pretty much to death. So this is using a different kind of range function, if you will. So if the iterable, so this part right here is called the iterable. If the iterable happens to be some kind of list, there's another function called enumerate, which counts the things in the list. And I think we will run this example because that one looks kind of cool to me. Hopefully that will copy paste okay. Create myself a new cell. Hit the paste meister. Insert the required spaces. Okay, so that's fine. Those need to be converted into proper lists. I'm going to leave the smart quotes in because I'm kind of curious what the computer will do with smart quotes in place. And here I'm having my mental troubles again. Go ahead and do that. Oh, okay, I see what's going on there. Alright, so what this should do is it should print the value of index 0, 1, and 2. And it should print the element associated with each of those index, the string quote 1, the string quote 2, and the string quote 3. Or it's going to give me the pink screen of failure. But we were successful. Alright, so that's 4 loops. And in practice, they're used for much more substantial structures than we're using for the examples here. So here's example 1 that I actually have already worked, and we'll go look at that in a second. So it says we want to add up all the numbers from 1 to some upper number, in this case 1 to 10. How would we instruct the computer to solve this problem? Now this seemingly simple example is actually extremely important. So the sum functions, the min functions that are built-in methods in various cases all work about the same way as we're going to demonstrate. So the way a human being might do it using pencil and paper would be to add the first 2 numbers together and store that as sum number 1, then add the next add the sum 1 to the next number, call that sum 2, and so on. So this sum 1, sum 2, sum 3, I'll call it an accumulator. And let's go take a look at it right here. Let me turn this to raw to kill the output, and then I'll return it to code. And so here's how simple it is to sum the numbers from 1 to n. So we want to, in this case, we want to know what n is, and so we're going to request a value for n. And then we set our accumulator to 0, so there's nothing in it. And then we simply use the range function, and we start counting at 1, because that's our test, sum from 1 up to n, which is how many, and it should be a positive integer, and we'll do it in steps of 1. So it's going to take the current value in the accumulator, it's going to add the value of I that we have used for the counter. Since we want to do floating point arithmetic, it'll float the I, and then it will put the result of that sum into the accumulator, and then it returns back to the top of the loop. So in this particular structure, we're using the counter both to count how many times we're passing through the loop, as well as a source of a numerical value to add to the accumulator. And then when we get to the end of the loop, we're going to print the contents of the accumulator and from 1 to n. Now this lets me introduce something kind of cool here. So right here I have a formatting code. And so it's got this %, dot 3f, and so what that says is represent whatever takes the place of the percent sign as a floating point number with 3 places after the decimal point. Then we have to provide what the percent sign means, and so this structure here says associate with percent the contents of the variable named accumulator, and so it's like it's putting the accumulator right where the percent sign is. I use this a lot, so you'll probably see it in a lot of my examples. There are hundreds of different formatting codes, so this is just one. So what it's going to do is it's going to print the output. It'd be like 1000.001 if that happens to be the output. So let me run the example, and now we'll pick a number, and see, the last max says go to 12, so 12 it shall be. And it claims that the sum from 1 to 12 is 78. Now we can cause a pink screen of errorness by entering a floating point number. I think this should confuse it. It's still going to integer that, so it'll just get the 11. Oh, good. That's what I was kind of hoping. So it can't handle the floating point number. So we have kind of a forced requirement to do it right. And earlier we saw how to do error traps to force me to get the correct number. So we could test that how many is a proper integer before we get the screen of pinkness here and get correct input. So let me rerun it correctly. I'm going to go to 20, no particular reason, and there we go. Okay, so let's look at the next one. So the other one is to sum all the even numbers from 1 to n. So I've interpreted the question somewhat differently. So we're going to get to use some other interesting functions. But let's say we're going up to 20, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. The main thing that's happening here is these are incrementing by 2's, and every single one of these numbers is divisible by 2. So if you do an integer divide, you get an integer result. Alternatively, if you use the modulo function, you'll get a 0 result, and we'll take advantage of that. So here's our next script. So this is going to do the even numbers from 1 to n. I'm quite aware that 1 is not an even number, but I have tested for that. So again, we have the how many input. We set the accumulator. We do the range from 1 to how many plus 1 in steps of 1. And so instead of taking steps of 2, I'm just going to test that every number that I pass by, because I already know this is going to get every integer, I'll just be sure it's an even. So I'm going to test the integer I. If it divides by 2 and the result of that modulo function is a 0, then I'll go ahead and accumulate. So I'll float the number, add it to the accumulator, put the result back into the accumulator, and then when I get done, I will have the sum of even numbers. So that's one way to do the problem. The other way would be to force it to start at 2 and increment by steps of 2, and then you don't have to do any testing. But it also means that if the numbers get big, you have no way of knowing if it got them or not. So we'll go ahead and run that. I'm going to put a 20 in again. So we know that if we sum just the evens between 1 and 20, it should be smaller than all the numbers between 1 and 20. And that's by the because theorem, which says because there's fewer numbers there and they end at the same point, they got to sum up to a smaller value. So got to do some math today. So the sum of evens from 1 to 20 is 110. And we can actually pick a smaller, let's just go to 6 because we can do that in our head. So the sum from 1 to 6 is 6 plus 5 is 11, plus 4 is 15, plus 3 is 18, plus 2 is 20, plus 1 is 21. So doing it in our head is 21. Now if we do the even numbers up to 6, we have 6 plus 4 plus 2. So that's 6 and 4 is 10 and 2 is 12. Ta-da! So we had a computer do what we could do with pen and paper. Moving along, this I thought was a pretty cool example. So it says print the triangle below and allow the user to enter the height of the triangle. So that's how many rows we want to enter. So we're going to do very crude console style graphics. And one way, if we need to print multiple values on a single line, we can use this print the symbol end equals null. And so what that means, by default, the print puts a new line character, and but I'm going to interpret the question different. I've interpreted it as we want to actually be able to make that triangle. So the height is how many rows, and for each row we print the number of stars that corresponds to the row count. So this one is row number 5. That's 5 stars. So let's take a look at this, because this is actually moving a little bit more advanced in our scripting skills. So first we do the how many, so that's going to give us the number of rows, and then I'm going to create a string variable called line to print. Now that statement creates a string variable, but what does that string variable contain at the moment that it's created? Someone unmute yourself and just say what it contains. You have no idea. It contains nothing. That's a null variable, but it is of type string. In fact, we can test that when we run it. It works better if I type correctly. Then I'm going to work through my loop. I'm going to go from 1 to how many plus 1 in steps of 1. And then what I'm going to do is I'm going to take advantage of this summing thing I just learned myself how to do. And I'll take line to print, and I will add to it the star variable. The character constant star. Now addition for a string does what? It actually has a different name. Anyone remember from a couple of meetings ago? So we have a string variable. We're using the plus sign, and then another string variable. What's that called?
Concatenation.
That's right, concatenation. And what it does is it takes the first variable and it joins them to the next variable. No spaces in between them. It just smushes them up together, and the result of that is a new string that's combined of the old strings. So what I've done here is I'm taking line to print, I'm smushing a star symbol into it, and I'm going to and I will send it back to line to print, so the new variable has the same old name, and then I'll print it. So what's going to happen is the first time it passes through this loop, line to print is null. We add 1 star to it, and then we print the 1 star. The second pass through this loop, line to print already has a star in it. We add a second star. When we print it, we print 2 stars, and so on. So let's just do 3. So we should get, the first row should have a, first thing it's going to do is going to tell us that the line to print is a string variable. Then it's going to print 1 star, and then a second star, and then a third one. Or it's going to do not. There we go. So let me suppress this output. And we will repeat the script. And now we can pick something. Actually, let's go big. You know, if you're going to go at all, we'll go big. And we now get half a Christmas tree. Actually, a quarter of a Christmas tree, because it's the upper half above the trunk, and it's one side of it. And that is that's that example. All right, moving into the other kind of loop, we have the while loop. And the while loop differs from a for loop in that the condition that's tested is we provide a condition conjecture, and it will perform the looped conditions while the condition remains true. And then once the condition becomes false, it exits. And the while loop is used for a type of repetition called sentinel controlled. And so we only execute the loop when the condition, here they're using fancy word, Boolean expression. So if you've never heard that, now you know what Boolean means, and so half of the science fiction romantic comedy movies will start to make sense to you. Really, if that was the only thing holding you back from enjoying the movie, that's kind of sad. But a Boolean expression or a logical expression is something that evaluates as true or false or can't evaluate, which would give you the pink screen of error. And then the statements you want it to execute. It still has the colon sign, and it still uses indentation as a scoping delimiter. It's possible to use a while else structure if that is advantageous. And let's repeat our 2 examples using a while loop to see the structure. So here's my while loop, and this case, we're going to sum numbers from 1 to n again. So we still have the how many, I still have the accumulator, and I've elected to use a counter. So I'll set the counter to 1, and then as long as the counter is smaller than the how many variable, I will take the contents of the accumulator, add it to the floated counter, and then store that result back in the accumulator. Now here, because I'm using a counter, I have to increment it as the programmer. So what that statement does is it takes the value of counter, adds 1 to it, and puts the result back in the counter. So I'm incrementing the counter rather than the loop is incrementing the counter. And this is a typical while loop. So let's see what happens if we were to enter a 10 and the counter's 1. Is 1 less than 10? That'd be a yes. So if that's true, then it's going to add the 1 to the accumulator, which starts out life as a 0. And so now the accumulator has 1 in it. It's going to take the counter and increment it from 1 to 2, and then return to the top of the loop, and then ask the question, is counter, which is now 2, less than 10? That'd be a yes. And it would repeat that until counter is larger than how many, because I have a less than or equal here in the test. and then we will print the result. So if I run this cell, ask me for, let's do ones we know the answer. Let's do ones we know the answer to. We know that 6 is 15. Excuse me, 21, the new 15. And that's the same result we got using the for loop, but a different structure. We'll do the same example with even numbers. I'll use the same computational thinking, which is I'm going to count through every number from 1 up to n, but I'm only going to accumulate the even numbers, and those are the ones where the counter is divisible by 2, or the modulo function returns a 0. So accumulator is again set to 0, we set the counter, and then we walk through the loop. If we run a 6 in that, we'll get a 12. So lo and behold, as expected. Let's go back up to 20 here. Remember, we should get like 200 something. I wonder what happened. All right, let me interrupt the kernel. Let me restart it. There we go. And I go down here, and then this is the evens counting, except that I think needs another deal. Oh, I know what I was doing. Show you what happens when counter's in the wrong place. So this is the same setup using just the evens numbers. Put in a 20. And we should get like 110. Or we get a stalled kernel again. That is weird. Oh, that's right. There's like 100 of us all. This is going to get annoying if it happens a lot. Kernel restarted. Well, that's no fun. Not what I wanted to click on. Well, my examples are no good if the kernel keeps... Oh, okay, that's my bad. I just created an infinite loop. That should work now. Let me go ahead and save that. All right, so here we test if it's even. If it's an even, we accumulate it. Then we increment the counter. So the incrementing the counter has to come outside the test. So I should have known that by having to interrupt the kernel a few times, I'd made a fairly fundamental program flow control mistake, but I assumed, usually correctly, that it was the computer's fault. So let's try that again. I'll rerun it. I enter the 20, and lo and behold, we get the desired output. Now the last example is again the Christmas tree one. It's the same structure, the same computational thinking. We're going to just keep appending to the line to print string the number of stars as we work through the loop. And we'll go ahead and put a 20. Cat, do not step on the keyboard. I'm doing class right now. By the way, welcome back. And there we go. So the last topic in the next few minutes is nesting. So in the Python language, actually pretty much any programming language, you can have loops that are inside other loops. Now there is a practical limit on the nesting. I don't know what it is for our CoCal. I mean, it's a combination of the computer's architecture, the available memory and swap space, as well as the language. But I would dare say for this class it's plenty. So maybe you can have 200 loops nested and it will still run. At some point, if you get too much nesting, it just fails and offers to take your credit card number and convert it to money. Still won't work. So this is a loop which is contained inside another loop. I have a cat. You really can't be here right now. Come on. So those of you that know the Bash scripting language, my cat is on the table executing cat. Okay, come on, guy. Well, I don't want you to bite me either. That wasn't me. Cat stepping on the keyboard. So yeah, you're getting the benefit of Dusty the cat, whose real name is Dusty Rhodes Traveling Cat, whose initials are DRTC, Dr. TC, the same as me. That was coincidence. I had no idea when I named him that. There we go. Okay, so we're in good shape now. Now he's just going to put his head on the keyboard. Okay, you can stay there, dude, and I can still do my job, all right? Okay, cool. Let me get back to where we were. Nested loops. So here's one example where it's printing from tables 1 to 10. I forget if I have a nested loop example. Looks like I don't. But you will have opportunity to use it at some point. So new loops can be nested. There's a couple of other important control statements. One is the break. Second is continue. And the third is pass. So the break statement is a way to exit a loop early and intentionally before you get to the end of it. And so sometimes we're executing a loop. Let's say we're summing up a series, which you've had in mathematics. So you have the sum of 1 to something, and it has a more complex expression than just adding it to itself. And when you get up to the point of that series where things start to become small, so there's no benefit to continue with a series, you want to exit the loop. But if it's an infinite series, you have to test for when the numbers are small and then exit. You break out of the loop. That's what the break statement's for. I believe there's an example in the laboratory. The continue statement is a statement that, when executed within a loop, will cause the loop to skip all the statements below it and immediately go back to the iteration test. And then the pass statement is literally a do-nothing statement. If you're familiar with other programming languages, the Python pass statement is very similar to the other programming languages' continue statement. But in strict Python, the two function quite a bit differently. The pass statement is used, think of it as a coding placeholder, where for some reason you need a place in your script, you need a line there that does nothing, that whenever it gets to that line, the script passes over it and moves on to the next line. And we'll see examples of that in the lab number 4. So that concludes the PowerPoint part, and we've looked at some of the Python loop lessons in my script, and let's look at some of these other examples. We'll take 10 minutes, and then we'll do our usual. Oh, that was scary. Looks like my computer is fixing to fail, because that's what they do best. Let's look at some other examples. So we've done that one, actually. We've done this one. We've done that one. We've done that one. We've done that one. Using a while loop. Oh, here's a clever one where he's incrementing backward. So this will be a fun one. Let's see if we can get this to go to. Okay, we get it to run. So my question to you all is, how do I turn that into an infinite loop? So somebody go ahead and unmute themselves and describe what they would do to make it an infinite loop. Change the greater sign. Well, let's go ahead and try that. That's the beauty of this. So while the variable is less than 0, go ahead and print it and then increment it downward. VAR is never less than 0 in our instance, but let's go ahead and run it. Not very interesting. So that clearly didn't work.
Can you make it var +1?
Yeah, that should have the desired damage. And it's just doing its thing. So let's go ahead and interrupt our kernel. Sorry, kernel. But yeah, we're using the Python 3 instead of the Sanders. Kernel Sanders is a great kernel. So hopefully I've regained control, and we will go ahead and return it to its correct structure. Yay. Okay, here's another one. That's the same example. Here's an example of nested loops. So good, I'm glad it's already scripted. Let me go ahead and turn it to raw, back to code. Okay, so here we're going to print a multiplication table from 1 to 10 using a nested loop. So the rows are going to start at 1 and end at 10. And then while we're in a row, it's going to multiply the row times the column count. So the column count is going to go from 1 to 10. And it's going to print the two values. So it's going to be n times m equals, I'm putting some spaces in so I think it'll be a little easier to read. And in today's lab, Farong might show you how to make those tables, this table a little bit prettier. So now we have our times table. So if we were all to go back to kindergarten, we're set, because we now can just program the computer to do what we had to memorize. Although the kindergarten I went to, we would memorize up to 12. And there are the times tables. So this is a pretty terrible way to represent multiplication tables. What would be cool would be to have rows going vertically, columns going to the left, and then the contents of the table containing the results. Here's an example of the break statement. So here it's going to start counting through the variable VAR. It's going to decrement it. If the variable VAR ever becomes identically equal to 5, it will exit the loop. and it exited that way. Let's go ahead and test. Let's see, 10. Let's test down to 2. We'll exit at 3. And now it's going to print all the way until 3 and then exit the loop. You have a exercise that's introduced in today's lab, which is some variant of that. Here's another example of a break statement as we're processing this list. If we encounter David, we break, because if you have a list with David in it, it's a terrible list. If anyone's actually named David, it's just an analogy. So this would break the loop and do something else. Here's another example. We can take the elements of the list and square them by simply processing them element by element. If we don't know how long the list is, we can use the length function and the range function to kind of do that automatically. And I'll run them both, but there's not much true to discuss here. Where the second one becomes nice is okay, so that should be an interesting output. It's gonna go 1, 4, 9, 16, 25, 64, 81, 49, 81, and then whatever 89 squared is. I don't know that. That wasn't in my times table in kindergarten. So we can have lists of varying lengths, and we can use the length function and the range function to let our loop execute regardless of the length. I'm pretty sure I didn't know how to multiply anything in kindergarten, but by second grade. Well, it's a long time ago for me, so I have no idea what they taught us back in the 1960s in kindergarten. But it was an easier time then. We just figured out how to get to the moon, and 9 years later we were going to make it. Cell phones didn't exist. Personal computers were a unrealized dream yet of the people that invented them. They weren't much older than me at the time. I guess they aren't much older than me now. There were no airbags in cars. We didn't have to wear seatbelts because seatbelts were an option that you paid extra for, so nobody had seatbelts in their car. What other interesting things can I tell you from the time when I grew up? But anyway, we still had to learn times table sometime between kindergarten and apparently second grade. Okay, I will prepare to set up the laboratory 4. So now would be a good time, if you have any burning questions, to ask them, and then I will hand off control of the video call to Farhang. See, I don't need that anymore. I'm pretty sure I had it together to already get lab 4 put up. Hopefully this is the corrected lab 4. Let me take a look real quick. This will be one of the few times I tell you don't pay attention to the screen. Oh, it doesn't even want to load. Okay, lab 4. Why is this? I have full Wi-Fi. I do not understand this at all. fine. Just go ahead and delete it. Oh, I think I'm in the wrong one. Yeah. We get in the correct course. There we go. All right. Okay, so that is still. All right, cool. Now it looks like I have control of the computer again. Going to the class bulletin board site and going to lesson 4, and then we will get back to the last example. There was a question on that. There are 2 quizzes. They're due next Wednesday. See if I can get to the correct lab 4. God, I hope that's the right one. Save link. There we go. Make sure this is the right one. Yeah, I think this is the correct one. Okay, so Max had a question on the last example. What's your question? It was something pertaining to A and C and why it was necessary. All right, here was the last examples, and the example started out as that and produced this list, and then I will extend the list by 2 elements. I'll run that example, and it does what's expected. And now watch what happens when I extend the list up here. Oh, it's probably going to do the same thing, actually. So the difference in the 2 methods are, this one is treating the list as an iterable, and by definition, it's going to step through each element of the list. So it's going to count 1, 2, 3. It's going to count the 7 elements and process them. In this one, we're basing it on the length of the list. Let me modify this slightly. Let's make that a 5. Now watch what happens when we do 5. It's only going to go take care of the 0, 1, 2, 3, 4. It'll only go up to 25, I think. Oh, even worse. Wouldn't kill me to do it right. There we go. So it only goes up to 25 even though the list is longer. So to make it automated, we have to have some way of determining the length of the list. And so the method suggested here is to use the range function on the length. Because we can't I don't think we can range the list itself. I'll try it. I don't know what's going to happen. I think it'll fail. Yeah, it has no way of ranging the list, but it can range based on the length of list. Except I need to be in the right place. Ta-da. And we could have fun. We could start from 1, see what happens. We can increment in steps of 2. And we get completely undecipherable output, but it works correctly. I would, I think at this point you want to avoid doing exotic stuff unless there's a good reason. All right, let's get set up for Lab 4. I'm going to make a quick change. I'll show you how to make it so that, oh, actually if you download the correct Lab 4, the typographic on the two is less than X. Oh, that is a typo. I want to fix this typographical error. So we go into edit mode and nothing happens. We try again. And we'll save that for when we get to exercise 2. Let me get it corrected. X plus 2, 4. Oh, that's weird. The remainder is set up to go. Let me quickly go through the lab, then I'll hand it off to Farhang. So today's lab is on program flow control. So it introduces count controlled repetition, which we've seen. Generally, the for loop is used for those. It shows you a structured for loop and some of these generic syntax. As you're working through, you might see cells that have this instruction. So that's to compact the actual lesson. So it tells you to change the cell to a code cell and run it. So if we change it to a code cell and run it, let me run these other ones first. And run it, it runs the cell. So here you would change to code, run the cell to do the example. Change to code, run the cell to do the example. Then it has your first exercise, which is to create your own loop. And the exercise is produce a loop that prints out all the leap years between 1900 and 1999 with the following information. 1904 was a leap year, and leap years from 1904 onward come every 4 years. And then put your answer in exercise 1. This is already set up as a code cell, so you can just type stuff here. Next one is sentinel controlled repetition, which is the while loop. Again, the examples, you have to activate them, run them to examine the examples, activate, run to do the examples. Then there's an example of nested. Again, you would activate the cell, run it, you can see what the effect is. Activate the cell, run it, see what the effect is. Now the writing that goes around these examples, it's intended for you to read it. So just running the examples and not paying attention probably isn't terribly useful. So for example, these two we just did. It says in the first case, the loop only executes 3 times before the condition j equals 6 is true. Then the loop's exited. The second case, j equals 7 never happens, so the loop completes all of its anticipated traverses. In both cases, an if statement was used within such a loop, and such mixed control structures are common and necessary, and it goes on to do some more explanation. You can also use loops to do some mundane activities. I'll let you do that in the actual lab. And then there's a second exercise. I've got to get the typo addressed, and I think Farhang's going to mention it during the exercise. And then here we want to produce output. When it says populate the table below, you just want to build a table that kind of looks like this. There's no expectation you're going to get the lines in place. That's not as necessary. Although Farhang has we'll introduce something called the pretty table module that kind of can facilitate that. And that's getting into introducing an idea that's we're going to spend more on next week. And exercise 4 is a modification of the other one. And then we discuss the continue statement. So I'll have to actually activate this and run it. And it tells you the message is skipped over when j equals 6. Here when it's 6, it skipped it. And the last and most important structure is the try except structure. And we'll say that for the actual lab. But this is a way to trap errors. And Farhang will explain it when it gets to that. And then your last exercise is stated here. And you're going to want to run, once you build your answer, you want to run it on 3 different cases. So I don't know a simple way to do that. One way would be to copy your answer into 3 different cells and run them individually. Or pretty much if it works for one as expected, it probably works for the other 2. So in this particular instance, you have a case where you're entering a string. So it's supposed to create an error, and you're supposed to trap that. In the next case, it puts these first 2 into integer form and floats the last one. The last case is just another example. So I will leave that to Farhang to explain. And let me hand over control of the meeting. Can't do it there. Oh, it's in people. That's where it is. Participants.